Now in next part of our water tank lecture, the theoretical part of water tank that I was covered in last lecture, as well as what are the assumptions made in working stress method that I was covered. Now I am going to concentrate some another theoretical part of a working stress method. So what is exactly the main difference between the stress block parameters, what we have studied in DCS1, the stress block parameters of a limit-state method, that is the Ku max, that is a constant of a neutral axis, Ru max, constant of a moment of resistance, and Pt max. Okay, like this you have to derive, like this you have to derive the design constants of balance section for the flexure in working stress method. That constant you have to use in design of water tank. That constant you have to use in the design of water tank. So first of all, I will tell you exactly how to differentiate the working stress method and limit state method by comparison of stress block, by comparison of a stress block. Okay, for that I want to draw the stress block here. For that I want to draw stress block here. Okay, so this is the it is the cross section view of a singly reinforced section. So this is the width of the section. Okay, so this is the effective depth of the section. Okay, already we have done in DCS1. Now we are going to concentrate on working stress method. So this is the area of steel. This is the area of tension steel. Already we know this. Okay, and this is the depth of neutral axis. So this is the depth of neutral axis. When you are going to consider the ultimate load condition, so to put here XU. Okay. Now, if you are going to consider the limit state method, previous one that we are considered in DCS1, okay, whatever we have considered in DCS1, that I am going to consider now how to plot the stress block. So the stress block is plotted. So I think this is the vertical line. Then you have to draw the stress block like this. Up to some extent it is straight line, then it is parabolic. In limit state method. Okay. So this exactly the highest it is 0.46 FCK. Already we know this. 0.46 FCK. Already we know this thing. Okay. Then the location of compressive force from topmost fiber is 0.42 axis. Already we know this. Okay, and the tensile force Tu is acting exactly at the center of the reinforcement. What is the difference between these two? The difference between these two is called lever arm. It is 0.42 XU. So these are the some parametric study of a stress block when you are going to consider the limit state method. Okay, so this is the stress block. Look the shape of the stress block. Up to some extent it is the rectangle, then it is parabolic. Already we know that 3/4 XU and it is already we have calculated the depth of the rectangular part, depth of the parabolic part. Okay, 3/7 and 5/7 of x. Okay. Now this stress block is considering the limit state method. Now when you want to draw the stress block by consideration of working stress method, how it is plotted? When you want to draw the stress block, when you are considering the working stress method, in working stress method, the main assumption of a stress strain graph of concrete under the bending compression, it is straight line. Under bending tension, it is straight line. Okay. So how you are going to plot? Extend the neutral axis. So this is your neutral axis. Now we are going to put here only x, not x, because it is a working stress method. Okay. And how it is plotted? So this is the high outermost fiber, compressive stress. Only you have to draw the straight line. Only you have to draw the straight line. So this curve is neglected. This curvature is not considered in working stress method because it is an ancient method. It is very oldest method. For simplicity they are assumed the stress strain graph of a concrete under bending compression. This is the concrete under compression. This is the concrete under compression. So for that the stress strain graph is considered as a straight line. For that the stress strain graph is considered as a straight line. Okay. Then what is the outermost fiber? So this outermost fiber is treated as a sigma CBC. Sigma CBC. It is a stress triangle. It is a stress triangle. Okay. And what is the depth of this triangle? It is x. And now the compressive force is acting exactly at the center of this triangle. The compressive force is acting exactly at the center of this triangle. From top, we know that the center of triangle is 1/3 of the base. 1/3 of the base x. Simple. From this it is 2/3 of the base. Okay. So this is x by 3. So simple it is written as a x by 3 from top. So the compressive force acting exactly at the center of this triangle, and the center of the triangle from the top is x by 3 because x is the base of the triangle. And the maximum stress, maximum fiber under bending compression is considered as sigma CBC. It is the sigma CBC is the maximum permissible bending compressive stress in concrete. Now where the tensile stress is acting? Obviously the tensile stress is acting at the center of the reinforcement. Center of the reinforcement is T. Now forward the U because U is for the ultimate, because we are considering the working stress, working load. So now if you want to extend this part, extend this part up to the bottommost, and this is the tensile force T. So what is this ordinate? This ordinate is maximum tensile stress in steel, and it is nothing but sigma ST. It is nothing but sigma ST. But this diagram is equivalent stress diagram. That means you have to convert the one stress in one material. Okay. So for that, conversion of this stress in tension in the form of a concrete stress, it is divided by modular ratio. Now this is the equivalent stress diagram. So this is the equivalent stress diagram. Equivalent stress diagram in form of a concrete. Okay. So this is the stress diagram in working stress method for the bending compression of concrete, and this is a stress diagram of a concrete under bending compression in limit state method. Now we are going to concentrating the stress diagram. Now we are going to concentrating the stress diagram under working load condition. So for water tank we are going to consider the working stress method. So you have to consider this stress diagram for derivation of design constant for balance section. Design constant for balance section, isn't it? Yes. So if you want to draw the stress diagram for the bending compression under working stress method, so how it is plotted? So simply it is straight line. Okay. Then you have to plot simple triangle. At topmost stability sigma CVC. Okay, and this is the x and this is the triangle. So this is the straight line of stress strain block of concrete under bending compression when working load is considered. Then we have to extend this. Okay, so this is the location of tensile force T, and this ordinate is sigma st by m. Okay, so this, why we are writing sigma st by m? Because we want to convert this stress into form of concrete. Okay, so at exactly at this CG of a triangle, from top it is x by 3, so compressive force. And now what is the difference between this? Difference between this is called the lever arm. It is denoted by Z. Lever arm is d minus, because this is a d minus x by 3. You have to write down here d minus x by 3. So these are the stress block parameters. Stress block parameters under working load condition. Working load condition. Notice sigma CBC. Sigma CBC is the permissible bending compressive stress. Bending compressive stress in concrete. Bending compressive stress in concrete. What is sigma st? Sigma st is the permissible tensile stress. Permissible tensile stress in steel, and these both stresses are defined in IS 456 on page number 81 and 82. Both tables are ready. Okay. Now I am going to derive the design constants for balance section under working load condition. Under working load condition. Okay, isn't it? Is it clear to you? Now, the first thing I am going to derive the design constants. Design constants for balance section. Design constants for balance section. Okay, that where we have studied in the CS1, RU max, KU max. Like this, you have to derive the same parameters, but you have to consider the working stress condition and this stress block. So first design constant is design constant for neutral axis. Design constant for neutral axis. As per our consideration, the symbol of this is K. Design constant for the neutral axis. Symbol of this constant is K. Now how to derive it? Now you have to take the consideration for this triangle and this triangle. You have to consider similar triangles. This triangle and this triangle. Base of this triangle is sigma CBC. Base of this triangle is sigma ST by M. Height of this triangle is x, and height of this triangle is I want to rub this down. Height of this triangle is d minus x. Okay. So how we are going to derive the design constant for balance section? The first constant is constant of neutral axis. Whatever we have designed in DCS1, this KU max, and formula for KU max is 700 divided by 1100 divided by something like that. You should know that formula. Okay. Same like that formula, you have to derive the design constants for neutral axis. Okay, and that formula of Ku max in limit state method is 700 divided by 1100 plus 0.27 Fy. Okay, like that you have to derive, because these constants are we are going to use this constant in design of a water tank elements. Okay, so first you have to consider these two similar triangles. So consider similar triangles. Consider similar triangles. Okay, this upper triangle and lower triangle. Okay, so the base of the upper triangle is sigma CBC. Sigma CBC. The base of the upper triangle is sigma CBC. Base of the lower triangle is sigma ST by m. Okay, height of the upper triangle is x, and height of the lower triangle is d minus x. From this, we are going to derive the formula K. We are going to derive the formula for K, and that is K nothing but x by d. That is K nothing. That is nothing but is x by d. Okay. Now what do you do? You bring this term here, that is m into sigma CBC divided by sigma ST is equal to x upon d minus x. Okay. So now I am going to rough this diagram. Okay, and I am going to continue this here. Now I am going to do the reverse of this formula. So how it is? This sigma ST divided by m into sigma CBC is equal to d minus x divided by x. Okay, because we want the term x by d, because I want the term x by d. So now what we have to do? Now, so this is sigma ST divided by m into sigma CBC is equal to d upon x. Okay, minus x upon x is 1. Minus x upon x is 1. Okay, so what we have to do? Now, what is here? D upon x is equal to sigma ST by m into sigma CBC plus 1, because I want to keep this term in this side, and d upon x I want to derive. D upon x. So now if you want to put the base same, okay, that is this term is, that is sigma ST plus m into sigma CBC. Okay, that is m into sigma CBC. Now this term I am going to convert like this. This term I am going to convert like this. Okay. Now the main requirement is x upon d. So we get d upon x. Now we have to again convert, reverse this formula. X upon d is equal to m into sigma CBC divided by m into sigma CBC plus sigma ST. Now how we are going to like this? Write x is equal to m sigma CBC divided by m sigma CBC plus sigma ST. Okay, into d. Now we know that x is equal to kd. We know that x is equal to kd. Now what is the k? So k is nothing but this term. K is nothing but this term. This term is m sigma CBC divided by m sigma CBC plus sigma ST. So this is the formula for k in working stress method. So this is the constant of balance section related to the neutral axis. This is the constant of balance section, design constant for the neutral axis. This in limit state method it is 700 divided by 1100 plus 0.27 Fy, and in working stress method it is m sigma CBC divided by m sigma CBC plus sigma ST, because this is the stress based method. Each and every stress is present in equation. Okay, sigma CBC is known. What is m? M is the modular ratio, and that modular ratio is defined in working stress method, and that modular ratio m is calculated by 280 divided by sigma CBC. 280 divided by 3 sigma CBC. Using this formula, easily we can get the modular ratio. Easily we can get the modular ratio. Okay, so this formula is now derived. Is it clear to you? Is it clear to you? Now, I am going to tell you the next constant is constant of lever arm. I will rub this. Constant of lever arm. Constant of lever arm. Okay. Second is constant of lever arm. It is simply called it J. Simply called it J. Okay. Now first you have to know what is the lever arm. So this is the stress diagram. Triangular. Okay. We know that this is sigma CBC. This is sigma ST by M ordinate. This ordinate is sigma ST by M. This ordinate is sigma CBC. Now the compressive force is acting here at the CG of the triangle. So this is, we know that x by 3 because this is x. Now this is the lever arm. Lever arm. Nothing but is Z. So Z is equal to d minus x by 3. Already I told you. So this distance is, we know that. So this is the d. So this d minus this, you get the lever arm. So what is the Z? So Z is d minus x by 3. So this is the lever arm. Now what is the constant of lever arm? So we know that just now we have derived the x is equal to kd. Just now we have derived x is equal to kd, and we know the formula k is equal to m sigma CBC divided by m sigma CBC plus sigma st. So you have to put this here. So z is equal to d minus kd upon 3. Now if you put d is common here, so 1 minus k by 3. Okay. So what is z? So z is equal to jd, and j is the constant of lever arm. J is the constant of lever arm. So what is the j? So this is the j. 1 minus k by 3. 1 minus k by 3. So this is the j. So this is the constant of lever arm. Isn't it? Simple. Very simple. Now the next important thing is how to derive the constant of a moment of resistance. Whatever we have derived in DCS1 is RU max is 0.133 FCK, 0.149 FCK, 0.138 FCK. Like this you have to derive, and these constants are required in design of a water tank elements. Okay. Now I am going to rub this. Okay. Is it clear? The last constant is constant of, third constant is constant of moment of resistance. It is R. Constant of moment of resistance, it is nothing but R. Okay. Now don't write U, because U is related to ultimate load theory. So we are considering here the working stress. So don't write U here. Okay. So now I want to sketch the beam. So this is the neutral axis. Okay. And this is the X. Okay. And this is the location of the steel. AST. And what is the stress block? The stress block is not triangular, simple to draw. Okay. So this is sigma ST by M. So this is the sigma CBC. Okay. Now what is the location of compressive force? From top it is x by 3, and this is the d minus x by 3, and This is the location of tensile force T. Okay. Now how to derive the constant of moment of resistance. So we know that what is the moment of resistance? Moment of resistance is nothing but the bending moment. What is the bending moment? Bending moment is nothing but force into perpendicular distance. I have told you so many times in DCS1. So bending moment is force into perpendicular distance. Now I am going to consider only one force, compressive force. If you consider the compressive force, so the compressive force C. Now consider the only compressive force multiplied by perpendicular distance. Okay. So what is the moment of resistance? Compressive force C and into perpendicular distance. Now what is the basic definition of force? The basic definition of force is stress into area. Stress into area. So what is the compressive force? So compressive stress into compression area into perpendicular distance. So which area you have to consider? The area is compression area. The area is compression area. So this area to consider. Okay. So this area is under total compression. This area is under total compression. So this area is B into X. This area is B into X. Right here B into X. Right here B into X is the area. B into X is the area. Now what is the stress? For this area, the stress diagram is triangular. For this area, the stress diagram is triangular. So you have to put the average stress. At top it is sigma CBC. At bottom it is 0. So you have to put the average. At top it is sigma CBC. At bottom it is 0. You have to divide by 2. You have to take the average because the stress variation is triangular. And what is the perpendicular distance? The perpendicular distance between the two forces is C and T is D minus X by 3. Is D minus X by 3, like this you have to write down. So this is the formula for moment of resistance when you consider the stress block in working condition. So what is the moment of resistance? We know that. So it is sigma CBC by 2 D into X into D minus X by 3, like this. Okay, isn't it? B into X is the area. Average stress is sigma CBC by 2. Sigma CBC stop at this location 0. Now it is very easy to find out the average stress in working stress method. Sorry. But in limit state method, the average stress of stress block is 0.36 FCK. It is given by the IS code. It is given by the IS code. But here, due to the linearity, you can directly write down the average stress. Now what you put? You have to put here X is equal to KD because just now we have derived this. So what is the moment of resistance? MR. So sigma CBC by 2 B, instead of X you have to put KD. Okay, and it is D minus KD by 3. Instead of X you have to put KD because already we have derived this. Now I want to rub this. Okay. Now the remaining part I am going to continue this here. What is the moment of resistance? It is sigma CBC by 2. Now put B as it is, K as it is. Now you have to take out D common from this bracket, then it is D square. Already D is there, and if you put the D common from this bracket, it becomes D square, and in bracket 1 minus K by 3. 1 minus K by 3. Okay. Now what do you have to do? Sigma CBC by 2 K. Okay. B D square, and now just now we have derived the 1 minus K by 3 is J. 1 minus K by 3 is J. So you have to put here J. So the formula becomes the moment of resistance is sigma CBC by 2 Kj BD square. Like in DCS1 RU max BD square. So like this sigma CBC by 2 Kj into BD square, Kj into BD square. Same thing we have derived here. So moment of resistance is equal to RBD square. This formula we are going to derive. Now what is the R? So the R is constant. R is constant for moment of resistance. So okay. So what is the R? R is this value. Sigma CBC by 2 into K into J. So this is the R. This is the R. Okay. Sigma CBC is compressive bending stress in concrete. K is the constant of a neutral axis. J is the constant of a lever arm. Okay. Like this, you have to consider the design constant for the balance section. Design constant for the balance section. Is it clear? Okay. Now, what exactly we have derived now? What exactly we have derived now? The design constants are in working stress method. Balance constants are, okay. First is the constant for neutral axis. It is K. So K is m sigma CBC divided by m sigma CBC plus sigma ST. So this is a K. Second is constant for lever arm. It is nothing but J. So J is 1 minus K by 3. Okay. And third constant is constant for moment of resistance. It is R. It is sigma CBC by 2 into K into J. So how we are going to use this? So this K we are going to use like this. X is equal to KD. This is Z is equal to JD. And MR is equal to RBD square. Like this, we are going to use this constant in design of a RC element of a water tank. Design of a RC element of a water tank. Now I will tell you what to do in design of a water tank. What to do in design of a water tank. So for that I want to sketch one diagram here. Okay. Let it be, it is a flexible base or rigid base. What to do? Okay. I want to draw this 3D view here. Okay. S. S. Very good. Now, what you have to design in water tank? First thing, you have to design the wall. First thing, you have to design the wall. So this is the wall of water tank. For that, you have to decide the thickness of wall. What is the thickness of wall? That it withstand the water pressure. The water pressure coming on this wall is like this. Okay. If the diameter of water tank is not given in question, you have to find out the diameter of water tank. If the diameter of water tank is not given in question, you have to find out the diameter of water tank by considering the height of water. By considering the height of water in tank. By considering the height of water in tank. So this is the height of water in tank. Okay. And this is the overall height of the wall. So this is the overall height of the ball. Overall height of the ball, height of the water in tank. Okay, you have to design the thickness of wall. Next thing, if the diameter of the tank is not given, you have to find out the diameter of tank by considering the total volume of water. Okay, in tank. Small h is the height of the water. Capital is the overall height of the ball. Okay, and this is the base slab. So this is the base slab. This also you have to design. When you are going to design the wall, the main thing is you have to decide the thickness of wall as well as by considering the water pressure, by considering the water tension or hoop tension is called hoop tension. It's called hoop tension. Okay, and the stepwise, first you have to decide the diameter of a tank if it is not given in question. First you have to decide the diameter of tank, internal diameter, considering the height of the water. Second, find out the hoop tension. Okay. Then find out the hoop steel directly. Okay. When it is flexible base. And then fourth is nominal steel. Okay. And fifth step, base slab design. And finally you have to decide the thickness of the wall. Okay, decide the thickness of wall. Okay, in flexible base you can decide the thickness of wall at any step, but in rigid base initially you have to decide the thickness of the wall. Okay, now I want to tell you how to provide the steel in the tank. So the hoop steel is provided like this. It is peripheral. Hoop steel is provided like this. It is peripheral. One in this face, another in this face, like this. One in this face, another in this face. One in this face, another in this face. One in this face, another in this face. So this is a hoop steel along the periphery of the tank, and they have to provide the nominal vertical steel. This you have to decide. What you have to decide? Diameter of tank, thickness of tank, hoop steel, that is peripheral steel, nominal steel, vertical steel. You have to decide. Okay, and finally you go for the design of a base slab. And maximum the base slab is designed nominally because it is resting on ground. There is no any predominant force acting on a base slab. So you are going to design the base slab considering the approximate dimension and approximate steel. Now I am going to tell you how to design the circular water tank resting on ground when it is flexible base. It is simplest one. Some 5 to 6 steps you have to follow, and then the design is complete. Now, how to design what are the design steps of circular water tank resting on ground when it is flexible base? When base is flexible, so there is no rigidity in between the base slab and wall, and at that junction there is no fixity, so there is no bending moment. you have to design the valve only for water pressure hoop tension. In the valve, only hoop steel is there and nominal steel is there. No any bending moment steel is present in flexible base. Water tank. Now, what you have to do in step number 1. If diameter of a tank is not given in question, if diameter of tank is not given in question, you have to find out the diameter of a tank using formula. So volume of water, okay. What is the volume? We know that it is the area into height of water you have to put here. Height of water you have to put here. Height of the water you have to put here. So we know the volume is equal to in meter cube. Okay, you have to put the area pi by 4 internal diameter square. So I am writing here DIA, diameter, internal diameter, and you have to put the height of water is small h. Using this formula, you have to find out the internal diameter of a tank. Okay, where V is equal to volume of water in liters. In meter cube. If the volume of water in liters given in question, you have to convert that liters into meter cube. That we know that 1 meter cube is equal to 1000 liters. 1 meter cube is equal to 1000 liters. Because if you excavate a 1 meter cube pit in ground, 1 meter by 1 meter by 1 meter, 1 meter width, 1 meter length, 1 meter depth, and if you put the water in that, exactly the water having the capacity 1000 liter. Okay, so 1000 liter is equal to 1 meter cube is equal to 1000 liter. To convert, if the volume of water given in liters in a question, you have to convert that quantity in meter cube. You have to put here and finally find the diameter of a internal diameter of tank, and small h is the height of the water. Already I was told you. So this is the height of the, and this is the base slab. Okay. So capital H is the height of the wall. Capital H is the height of the wall, and small h is the height of the water. Small h is the height of the water. You have to put here small h, and the remaining part is called a freeboard. Remaining part is called a freeboard. So if the freeboard is not given, you have to assume the freeboard in between 0.2 meter to 0.5 meter as per your convenience. And if the height of water is not given in question, you can assume this small h, 2 meter, in between 2 meter to 4 meter. If the height of water is not given in question, you can assume the small h in between 2 meter to 4 meter. So in step number 1, you have to find out the internal diameter of a tank. Then directly go for the calculation of a hoop tension. Okay. Step number 2. Directly go for the calculate hoop tension, and that hoop tension is called T, and that hoop tension generated by the T, having the formula T is equal to gamma W into internal diameter of tank into capital H divided by 2. Using this formula, you can find out the hoop tension. Now you have to put capital H. Now to put here capital H is the height of the wall. Capital H is the height of the wall. And height of the wall. And gamma W is the density of a water. If it is not given, you assume it is 10 kilonewton per meter cube. If it is not given in question, you can assume it is in between 10 kilonewton per meter cube. Small d is the diameter of tank, internal diameter of tank, already we have calculated it. Capital H is the height of the wall. If it is not given, you can find out it. From this you can find out the hoop tension which is acting on this wall like this. The hoop tension is acting on the wall like this. Because this is a flexible base, so at base there is no bending moment, so only you have to design the wall for the hoop tension. Now, step number 3, calculate hoop steel. Calculate hoop steel. It is called a AST hoop. It is called a AST hoop. So how it is calculated? T divided by sigma ST. So this simple step. T divided by sigma ST. Using this formula, you can find out the hoop steel. T is the hoop tension. What is sigma ST? So sigma ST is the permissible stress in steel. It is the permissible stress in steel due to hoop pressure. Okay, due to hoop pressure, due to hoop tension, due to water pressure, and as per 3370, as per IS 3370 part 4, it provides the value of sigma ST for Fe 250 and for Fe 415. Fe 250 and for Fe 415. Value of sigma ST. Value of sigma ST is for Fe 250. It is 115 megapascal. It is 115 megapascal. So there is no need of another column here. Sigma ST. And for Fe 415, it is 150 megapascal. Only you have to remember this. You have to put this value in the formula and find out the hoop steel and provide peripherally. Okay. Now, what you have to do? Now, what you have to do in step number 3? Assume the proper diameter of a bar. Assume the proper diameter of a bar and find out the spacing now for this hoop steel. So assume diameter of a bar. Assume diameter of a bar. Assume the diameter of a bar. And now to calculate the spacing. Don't calculate the number of bars because here number of bars are there. So many number of bars are there. So you have to find out the spacing. Spacing is calculated 1000 small st divided by capital ST like this. Whatever I was done in design of a slab, that you have to do here. Okay, is it clear? So to find out the spacing of the bar. Find out the spacing of the bar. Once you get the steel, you have to find out the spacing of the bar. Okay. So we know that small AST is the area of one bar. Small AST is the area of one bar, and capital AST is the total tension area. Total tension area. Okay, like this you have to find out the steel. Now, how to find out the how to find out the how to find out the minimum steel? How to find out the thickness of the ball? This is step number 4. Step number 4. How to find out the thickness of the bar, thickness of the tank? Step number 4. Calculate. Calculate thickness of wall. Repeat steel. This is one formula. It is capital T is equal to it is 1000 into small t plus m minus 1 into HT hoop into sigma CT. So this formula is the equivalent area formula. This formula is the equivalent area formula. Using this formula you can find out the thickness of the tank. Okay. Capital T is the hoop tension, small t is the thickness of the tank, m is the modulus ratio. Already we know that. HT hoop is already calculated in previous step. Sigma CT is the permissible sigma CT tensile stress in concrete. Permissible tensile stress in concrete, and this stress is not clearly mentioned in limit state method. That's why we are using the working stress method in this design of a water tank. Okay, now what is the T? T is the hoop tension, small t is the thickness of wall, small m is the modular ratio. We know the formula, it is 280 divided by 3 sigma CBC, and this sigma CBC we are using from IS 456. It is the bending compressive stress in concrete. This sigma CBC we are going to use from IS 456 2000 version, page number 81. Okay, I think it is on page number 81 is the table. Okay, you have to use the sigma CBC. Sigma ST, it is defined in IS 3370, and sigma ST also it is defined in IS 3370. Okay, so you have to use this formula for calculation of thickness of tank. What is the sigma CT? So sigma CT is the permissible stress in concrete. Permissible stress in concrete, and it is tensile stress. It is tensile stress. Okay, permissible tensile stress in concrete. And what are that values? I want to write down here. Concrete grade and sigma CT. Concrete grade and sigma CT. That values are for M15, for M20, for M25. I have that values, and for M30, okay, and for M40 and above, M40 and above. Okay, so it is 1.1, 1.2, 1.3, 1.4. Sorry, it is 1.5. 1.1 for M15, 1.2 for M20, and 1.3 for M25, then 1.5 for M30, and above 40 is not applicable. If you consider the tracker section, so it is not given in IS 4. Okay, so you have to put the sigma CT value here and find out the hoop tension T. But remember that the thickness of wall is should not be less than 150 mm. Should not be less than 150 mm. If it is less than 150 mm, you have to provide the minimum thickness 150 mm for the thickness of the wall. Okay. This is step number 4. Now last step number 5. What are you doing in step number 5? In step number 5, find out the nominal vertical speed. Finding nominal vertical speed, because the vertical speed is only for to keep the proper spacing for the main steel. So this is the wall. Okay, I want to show you here. Okay, and this is the main steel. This is the main steel. Okay, and this is the nominal steel. So this is the vertical nominal steel. What we are going to, so this is the vertical nominal steel, and that vertical nominal steel is called the AST minimum steel. AST minimum is, as per the IS 3370, it is 0.3% of gross cross sectional area of concrete. Gross cross sectional area of concrete. It is 0.3 divided by 100 into what is the gross area of concrete? If you consider thickness is T, into length of the, into peripheral length of the tank, it is considered as a 1 meter. It's considered as a 1 meter. So T into 1 meter. T into 1 meter or T into B width of the or peripheral width of the wall, and B is the 1 meter. You have to put here 1000 mm always for this calculation. You get the value. You get the value in mm square. Step number 6. Last step number 6. How to find out how to design the base slab. Okay. Design of base slab. Base slab is designed as approximately. Assume the proper thickness of base slab. Assume proper thickness for base slab and provide the minimum steel. And provide minimum steel. Like this, you have to design the flexible base water tank resting on ground.